So let us today discuss about stresses in composite members as a part of our lecture number 7. Okay, so let us see what are composite members or compound members. So composite or compound bars members are the members which are made up of two different materials or more than two materials. Okay, so if a particular member is made up of two or more different types of materials, then such a member is called as composite or compound bar. So, as you know, the usual example for such a kind of compound bar is concrete column. Okay, if you see the column is made up of concrete, which is a material one, and steel rods, okay, steel bars, which is a material two. So, two different kinds of materials are together forming a member, a column. Okay, so now whatever the load is coming onto that column are being shared by the concrete and the steel also. Okay, so now we are going to see that such a kind of composite or compound parts. Okay, and there are two situations in which these members can exist. Okay, as you can see, this is the case 1 and this is case 2. Okay, in the case 1, a load is being applied, and in the case 2 also. The difference between these two is the length of material 1 and material 2. Okay, remember that the length and dimensions of these materials may not be the same. They can be whatever they want. Okay, they can be of any cross sectional area, any length. Okay, but whatever the load is applied on those members, okay, on that member, okay, will be shared by those two materials in some proportion. Okay, they are not going to share that load equally. Okay, for example, if P is the total load acting on this composite member, the material 1 takes a load of P1 and this material 2 is going to take a load of P2. So now the total P load is equals to P1 plus P2. So this is going to happen, and P1 can be equals to P2, but that is not necessary, and most of the times P1 is not equals to P2. Okay, so don't care about that, that is not much importance here. Okay, but remember this equation, this is the first equation. Okay, P equals to P1 plus P2, and remember that the ends of the different materials of the bar are held together under loading conditions. Okay, these are held together. Okay, if these two members has to take load at the same time together, then those materials have to be together bonded with a plate or something like that. Okay, and as you can see in this picture, the length of both the materials is the same. Okay, so something like this. See, concrete and steel, generally in a concrete column, okay, the length of the concrete portion and the steel bar are going to be the same. Okay, remember that. Okay, but there are also cases where any two members may not be same. Okay, so that is what I want to say. And the other important thing here is, okay, as these two materials are different, they have different properties and they undergo different amount of change in length for a given load. Okay, practically, I mean, if they are separately dealt. Okay, but when they are behaving as a composite member, when they are coming together to form a single member, okay, their behavior is going to be changed a bit. Okay, in what way is the increase in length in the material 1 and material 2 surely going to be the same. Okay, as you can see here, okay, the change in length is same. So change in length is nothing but delta L, that is how we represent. So I wanted to tell you that if this is the material 2 and this is the material 1, so delta L1 is equals to delta L2. Okay, change in length in material 1 is equals to change in length in material 2. Of course, it is a tensile force. Then increase in length in material 1 is equals to increase in length in material 2. And if it is a compressive load, then decrease in length in material 1 is equals to decrease in length in material 2. Okay, so what I wanted to tell you is we have obtained two equations from this criteria, isn't it? The first one is the whatever the load that is being applied on this composite member, the individual materials, material 1 2 3 4, whatever, how many materials can be there, okay, those materials are going to share that load. Okay, that sharing of load may not be in the same proportion, అంటే సగం సగం half of తీసుకో. Okay, it happens rarely. So different proportions load depends upon the kind of material, area, and how it is placed and everything. Okay, so now this is what you need to understand. And the next thing is the change in length is equals to each other. Okay, material 1 and material 2, the change in length is same in both. And the third one important point is the strain. Okay, for example, epsilon 1 is equals to epsilon 2, this may not be equal. Okay, even this change in length is equal, the strain may not be equal in all the cases. For example, as you see in this first figure over here, okay, what is the epsilon 1 is equals to delta L1 by L1, and second one is delta L2 by L2, isn't it? So as you can see, this is E3, right? So as you can see in this figure over here, even though the delta 1 and delta L2 are equal, okay, this L1 and L2 are not equal. The length of these individual materials is not the same, right? L1 is not equals to L2. So this is L1 and this is L2. Okay, both are not same. Therefore, these strains cannot be same. But here in this case, strain 1 is equals to strain 2. Okay, because these are of same length. Okay, let me just go to the next slide. So see, if P is the load that a member is carrying, composite member, okay, and if that material is made up of material 1 and material 2, two kinds of materials, then the load acted on it is being shared by the material 1 is P1 and material 2 is P2. Therefore, P1 plus P2 will be equals to P for sure, isn't it? So since the ends are held securely, we get delta L1 is equals to delta L2. Okay, delta L is equals to delta 1 is equals to delta L2. Of course, we know these dimensions, isn't it? Delta L is equals to PL by AE, as we have 2, and just use the suffix here. P1 L1 by A1 E1 is equals to P2 L2 by A2 E2. Okay, so what happens is if the length is same, length of both the members is same, this L1 and L2 is getting cancelled, and as you can see, this is force by area and this is force by area. Force acting on material 1 by cross-sectional area of material 1, force acting on material 2 divided by area of material 2. So what you get is P1 by A1 is equals to stress in material 1 divided by E1 remaining part, which is equals to P2 by A2 is nothing but force acting on material 2 by its area. So sigma 2 by E2. So that is what we wrote over here. Okay, sigma 1 by E1 is equals to sigma 2 by E2. This happens only when the length L1 and L2 are same. So let me explain you how we analyze these compound bars with a simple example. Okay, analysis in the sense we are trying to find out what is the stress and strain and elongation in the body in the compound member due to the externally applied forces. So let us take a problem over here, problem number 9 as per our numbering and based on compound stresses. So here is the question over here. So as seen earlier, better write given data at the beginning so that you don't get confused. So write the given data and draw a rough figure of the problem. Okay, then it will be simpler for you to completely solve the question. As you can see here, um, a short rightmost concrete column 600 by 600 mm. I mean, this is the column 600 and this is 600 mm, has 8 rods. Okay, this is a cross sectional of the concrete column, therefore I can see the cross section of steel bars also here. So how many are there? 8 bars, and each has a diameter of 25. Okay, see, I told you in the previous class that diameter is also denoted by 5. So as reinforcement, find the stresses in the steel and concrete. I mean, he's asking to find out sigma s and sigma c and elastic shortening of the column delta L. If E is equals to 200 gigapascal, 2 into 10 to the power of 5 Newton per mm square for steel, and for concrete is 10,000 Newton per mm square. Load acting on that column is 3000 kilonewton and length of the column is 3 meter and E is equals to this value. So as you can see, the simple thing he asked is, there is a column here with a particular cross section. There are 8 bars of particular cross section, and now a load of 3000 kilonewton is being acted upon this compound or composite member. The length of the column is 3 meter. Okay, so he asked you to find out what is the stress in the steel, what is the stress in the concrete, and what is the change in length. Here the change in length is going to be contraction. Okay, contraction, because he said clearly shortening is nothing but decrease in length. Okay, so this is a compressive load, therefore the member is going to contract, so the change in length is going to be decrease in length. Okay, so now let us find out sigma s, stress in steel, sigma c, stress in concrete, and delta L, elastic shortening of the column. Okay, so here delta LC is nothing but change in length in concrete, which is equals to delta L of steel, isn't it? But this can also be written as just simply as delta L of column. Okay, why can you write this? Because both these materials are of same length, isn't it? Therefore, as delta L1 is equals to delta L2, the decrease in strength in column, I mean concrete or steel bars, is equals to actual change or decrease in length of the column, isn't it? Okay, so that is how we write, and that is why he asked to find out the elastic shortening of column. So let me go to this solution for you. So here is the solution. So PC and PS are the stress loads acting on that body. Therefore, from the first equation of equilibrium of forces, PC plus PS is equals to 3000 kilonewton. That is 3 into 10 to the power of 6 Newton. So this is the total load acting upon the column, and this value is being shared by concrete and steel. Okay, so this is the cross sectional area of the steel. Okay, pi divided by 4 into d square. okay, cross section of each bar into 8 gives the cross sectional area of steel bars of 8 bars. Okay, now the area of concrete is 600 into 600 minus of area of the steel, right? This is nothing but 600 into 600 is concrete area, column cross sectional area, but the column cross sectional area is nothing but sum of concrete area and steel. So this is steel area, and take that area from column, you get concrete cross sectional area. So why are we calculating these areas here? So in order to calculate the loads, okay, and the stresses over here, which you need to find out, these areas are very much required here. And as you see, the strains in the two materials are equal, that is PC by AC is equals to PS by AS ES. So that is what we have seen earlier, because the concrete and steel has the same length, isn't it? Generally delta L1 is equals to, delta LC is equals to delta L. Yes, since both have the same length, ES is equals to EC also. Strain in concrete is equals to strain in steel. So that is what we have written over here. Delta L1 is equals to delta L2. Okay, PL by AE is equals to PL by AE. But here this is LC and this is LS. As both are same, these are going to be cancelled. Okay, length of the concrete is equals to length of the steel, so they get cancelled, and this is what you get equation. Now write PC is equals to in this manner. Just send these two parameters onto the right side. Substitute all the values in this expression, you will get this. PC is equals to 4.5336 PS అనే వస్తుంది value. Okay, now you know PC is equals to this in terms of PS. Okay, so now substitute this value over this equation. PC plus PS equals to 3000 into 10 to the power of 6 Newton. So you will get this equation, and now substitute them, and you get PS equals to 542 kilonewton and PC equals to 458 kilonewton, isn't it? So this is how you found out the loads being shared. How, if you add these two, you are going to get 3000 kilonewton, isn't it, right? So now these are the PS and PC values. Now you can calculate the stresses in each concrete and steel, isn't it, right? Force divided by area. So that is what we have done here. Okay, compressive stress in concrete is equals to force by area of concrete, and compressive stress in steel is equals to cross sectional area of steel divided by its area, this value. So now we need to find out what is the shortening of length. So delta L is equals to PL by AE. So here delta L is actually is equals to delta L1 is equals to delta L2, isn't it, right? So you can use in terms of steel or in terms of concrete, you can write the formula. That is, you can write delta L is equals to PC by LC by ACEC, or is equals to PS LS divided by ASES. Okay, so I have used this formula, so I'll get this value, same value. If I used this formula also, I'm going to get the same value over here. Okay, so this is how we calculate the change in length also. Now let us do another problem, which is here. Okay, so this is also a problem similar to the previous problem. So I just wanted to make sure that you are habituated with using the fundamental equilibrium equations here. P equals to P1 plus P2 and delta L1 equals to delta L2. Okay, so you need to get used to that formula. Simple formulas, isn't it? You just need to remember them. So now let's see this question over here. A compound bar of length 600 mm consists of a strip of aluminium and thick of steel some portion. So there is a compound bar of length 600 mm consists of strips అంటే చిన్న చిన్న ముక్కలు. Okay, చిన్న wooden strips laga. So those strips, see, this is the aluminium strip and this is the steel strip. They have same length, and 600 mm is the length, and aluminium has a cross-sectional area of 40 mm width and 200 mm. So what is the area of aluminium? 40 into 20 mm square. Thickness of the steel strip is 60 mm wide and 15 mm thick. Okay, so these are both rigidly joined together here, rigidly fixed, and there is a load acting on this body 60 kilonewton. So what it is asked in the question is stress developed in each material and also the extension of the compound bar. Okay, so that this is what we have done previously in the previous class also. Okay, so let's do the same thing, just make sure you understand this concept. So this is the given data, length of the bar and load acting on the bars, member, and cross-sectional area of aluminium and steel strips, and Young's modulus. So take care that you substitute proper Young's modulus. Don't just put the Young's modulus of aluminium in place of steel. Okay, don't get confused in such a way. So the first equation is if a P, okay, let this be P. If P 60 kilonewton is acting on this composite member, this steel strip and aluminium strip both are going to share load. So if this is P1, this is P2, okay, the load taken by this is P1 and this is P2. So by adding these two, you get the total value over here, isn't it? Right? See, PA plus PS is equals to 60 into 1000. From compatibility equation, we have delta A is equals to delta S, isn't it right? You can write it as delta LA equals to delta LS, okay, as per our denotion over here. Okay, so the increase in length in steel strip is equals to increase in length in aluminium strip. So that is what this condition is telling us. Okay, this is the second condition, isn't it? So this is how we write, isn't it? Delta L is equals to PL by A. So as L is same, you can just cancel them. Okay, these get cancelled, and so solving this equation, you get PS value in terms of PA. Okay, Randy. So now put this PS in the previous equation over here. So here see, PA plus PS is equals to 60,000. So put that value over, okay, this value over that equation, and you get PA plus 2.25 PA equals to 60,000. So by solving, you get PA and also PS from that equation, isn't it? So now the stress in aluminium strip is load taken by aluminium strip divided by its cross-sectional area gives the stress in the aluminium, and stress in steel strip is also given by load acting on the steel strip divided by its area, 46.15 Newton per mm square, and the extension of the compound bar is equals to PL by AE. You can write this as PS LS divided by AS. Yes, also you can substitute those values and still you are going to get delta L is equals to 0.138 mm. So let me give you a brief, a simple problem for homework. So I hope you understood the previous two problems, and they are going to be very easy, isn't it, right? So this is a similar kind of problem. What you need to find out is the stress is developed in both the materials. Okay, calculate the stress in the copper, sigma Z and sigma steel. Okay, same concept as we did earlier, and verify these answers. Okay, so with this I am concluding this topic. Okay.